Hey everybody in Calc BC. Today we are going to be learning about lesson 5.2, integration through partial fractions. If you take a look at College Board's version of the curriculum, again, we are going to be doing 4 different lessons in this unit, and this is the second lesson. It comes from College Board's Unit 6 about integration. You can see right here, we have using linear partial fractions, and that's what we are going to be covering today. And you might remember the idea of partial fractions from honors pre-calc, or I don't think that regular pre-calc covers it. So if you had that, then you might not have seen this before. So we're going to go over just the basics of what finding partial fractions means first before we apply it to integration. And you can see right down here, we've got the more detailed version from College Board that says the essential knowledge is some rational functions can be decomposed into sums of ratios of linear non-repeating factors to which basic integration techniques can be applied. So that's what we're going to be looking at today. Let me switch over to notes. All right, so here's our notes for the day. First, we're just going to read through what this says at the top to make sure we understand. Integration by partial fractions. Although textbooks cover many more complicated techniques for partial fraction decomposition, the AP exam only covers non-repeating linear factors with integration. In pre-calc, we actually did cover more complicated techniques. So we're going to talk about the type of partial fractions that we need for today. Clearly, neither use substitution nor integration by parts will work effectively for this integral right here. We're kind of stuck. There's no u and du. There's no two things multiplied that we can easily derive or integrate to make that easier. So we're kind of stuck. We could complete the square in the denominator and use trig substitution techniques to get a solution, but this is not efficient, and trig substitution is not part of the BC curriculum. So instead, we will utilize partial fraction decomposition to create a more simplistic integral. So here's just a reminder of partial fraction decomposition. So what we do is, the goal is to, kind of decompose a more complicated fraction into two or more manageable fractions with linear denominator instead of a quadratic. Okay, so that's what we're looking for. So to start, we factor the denominator. So this denominator factors into x minus 3 times x minus 4. And then we split it into two fractions. One has the denominator x minus 3, and the other has the denominator x minus 4. We don't know a and b yet, but those are constants in our numerator. So by multiplying both sides of this equation, right here, if we just think about this as our equation, and we multiply everything by x minus 3, x minus 4. On the left, you'll see that this and this cancel, and this cancel. So we're just left with 1. On the right, if we distribute the x minus 3, x minus 4 to each numerator, the x minus 3's will cancel from the first fraction, so we end up with a times x minus 4. The x minus 4's cancel from the second fraction, so we end up with b times x minus 3. To solve for a and b, which will be important for our final answer, we simply choose convenient x values that will allow us to solve quickly. So when x equals 4, so we're going to set x equal to 4 because that will set this factor equal to 0. So that's what we're going to start with. We call those our convenient x values. So we're going to have 1 equals a times 4 minus 4 plus b times 4 minus 3. And 4 minus 4, as we know, is 0. So we have a times 0. 4 minus 3 is 1. So the a goes away, so we get 1 equals b. When we plug in x equals 3, what are we going to get? 1 equals a times 3 minus 4 plus b times 3 minus 3. So we get a times negative 1 plus b times 0, or 1 equals negative a, so negative 1 equals a. All right, so that means we can rewrite our original with the a and the b plugged in. So we can combine this to have, what was a? Negative 1 over x minus 3 plus 1 over x minus 4. And that means that if we have this as an integral, we can rewrite as two separate fractions. And that makes this much easier to solve, okay? So now we're going to integrate each of these fractions separately. You can use U substitution for the denominator. And what's going to happen is we're going to end up with, you know what, since this is the first one, I'll write this out a little bit more in depth. So we're going to have negative the integral of 1 over x minus 3 dx plus the integral of 1 over x minus 4 dx. Each one of those fractions is just going to become the natural log of the absolute value. So that for the first one, we're going to end up with negative natural log of absolute value of x minus 3. For the second one, we'll have natural log of absolute value of x minus 4. And this needs a plus c at the end because we don't have bounds. Okay? So that is how we use partial fraction decomposition to help us integrate a complicated looking fraction. And as I said, in honors pre-calc, we looked at much more intense partial fraction decomposition than this. But for Calc BC and integrals, we only need non-repeating linear factors, meaning the x minus 3 and the x minus 4 each only show up once, and they're both linear. They're both, you know, only x's, no x squareds, no x cubes. So that's what we're going to be talking about and working with here. There is, however, an easier way to determine the a and the b values. So I'm going to set this up one more time to show you what we call the cover-up method. And I am not positive. If you had me, I may or may not have shown you this back in honors pre-calc. So let's take a look and I'll show you how we do this. It'll save you a lot of time. So I'm going to just set up our partial fractions without writing the a and the b in the numerator. So it looks like that. And here's what we do. I'm going to write out the steps over here so that you can follow them again later when you come back and look at your notes. So what we do is we set a factor equal to 0 and solve for x. That part is kind of similar to finding the convenient x values. And then we cover up the corresponding factor in the original fraction and plug x in to everything else. And that's going to give us our new numerator for that term. So let's start with the x minus 3. So if I plug x, if I want to set this factor equal to 0 and solve for x, I would get x equals 3, right? Because 3 minus 3 is 0. So what I do is in this fraction, the original fraction, I cover up the x minus 3. Think of this now as just 1 over x minus 4 and plug that 3 in for x. So we would get 1 over 3 minus 4. So I'm getting 1 over negative 1, which is negative 1. For the numerator of x minus 4, I think, okay, the convenient x value here is going to be positive 4. I cover up the x minus 4, and I think of the rest of this as a new fraction, plug in 4 for x, and I get 1 over 4 minus 3, or 1 over 1. So I get positive 1. And you can see we got the same answer. Then we would be ready to integrate. So we're going to practice this a couple more times with a couple more examples. All right, here's a review of what's on the AP exam. On the AP exam, all partial fraction integration questions will only use non-repeating linear factors, similar to the initial example. Often, the integrand will already be factored in the question. So the denominator will already appear factored most of the time. Excuse me. You will need to practice identifying these problems and distinguishing them from U substitution and inverse trig integrals. So, you know, on the AP test or on a final, you're not going to know automatically that this is partial fractions. It's not going to tell you in the question. You're going to have to kind of think through, okay, is this U substitution? Is it inverse trig? Is it partial fractions? So let's try a couple more examples. These ones are straight from former AP exams, so you can tell exactly what was on the test. All right, so for this first one, we have 2x over x plus 2 times x plus 1. So we're going to separate this into two different fractions, something over x plus 2 plus something over x plus 1. And so I'm going to jump straight to the cover-up method. So for this x plus 2, I know that x would have to equal -2. So I'm going to cover up the x plus 2 over here, plug in -2 for the rest of the x's. So we have 2 times -2, so -4 on top, -2 plus 1, so -1 on the bottom. So -4 over -1 is going to be 4. And then for this one, the convenient x value is going to be -1. So cover up the x plus 1. We have our new fraction over here. 2 times -1 is -2. -1 plus 2 is 1. So -2 divided by 1 is going to be -2. So we found our partial fractions. Now we have to integrate. So we could write out another step where we pull out the 4 and the -2 if we want. Looks like this. And then our last step is going to be to actually do the integral. So we're going to have 4 times the natural log of the absolute value of x plus 2 minus 2 times the actual log of the absolute value of x plus 1 plus c. Not too bad, right? All right, our next one is from the 2008 BC exam. 2008 is actually when I took the AB exam. I took the actual exam that year when I was in high school, but I never took BC in high school. My high school didn't offer it, but I took Calc 2 my freshman year of college. But here we go. So the integral of 7x over 2x minus 3 times x plus 2. This one's also already factored for us. So this time we are going to split it with one denominator as 2x minus 3, and the other denominator is x plus 2. So let's try that cover-up method. This time for 2x minus 3, if we set that equal to 0, it's a little bit more complicated because we have a coefficient here. So we add 3 and divide by 2. It's going to be 3 halves. Okay, so let's think that through. We are going to cover up the 2x minus 3, plug 3 halves into everything else. I'm going to write it over here because this one has fractions. So we have 7 times 3 halves over 3 halves plus 2. So let's try that. We get what? We have 7 times 3 is 21 over 2 over 3 halves plus 2. So 2 is going to be 4 halves plus 3 halves is going to be 7 halves. So both of these have a denominator of 2, or I could just write it as 21 over 2 times 2 over 7. The 2's cancel. 21 divided by 7 is 3. So that actually turned out pretty nice. Our first numerator is 3. For the second one, the convenient x value is going to be -2. So I cover up the x plus 2. 7 times -2 is going to be -14. 2 times -2 is -4. Minus 3 is -7. So I get 2. Okay, cool. So now we are ready to do the integration. Once again, I'll just write this step out. And this time we're going to have to think through that the x has a coefficient in the first one. So if we did the U substitution, what you would see is you're going to have to multiply your final answer by 1/2 to account for the fact that if we were taking the derivative, we'd have to use the chain rule. So what that means is we're going to have 3 times 1/2 the natural log of the absolute value of 2x minus 3. I'm not going to write out the u substitution, but you can if you want to. And the second one is just normal, 2 times the natural log of the absolute value of x plus 2 plus c. So we could rewrite this as 3/2, but that's essentially the same thing. So we are finished. And finally, the last question from the 2012 BC exam, the international version, it looks like. Now we have an integral from 0 to 1 of 5x plus 8 over x squared plus 3x plus 2. This one's definitely the most complicated because the denominator is not factored yet. And we have bounds, so we're going to have to work through all of this. So let's see what we got. So x squared plus 3x plus 2 factors to x plus 2 times x plus 1. And so let's find the partial fractions. Okay, so we'll go back to this step. So the first convenient x value is going to be -2. I cover up the x plus 2. 5 times -2 is -10 plus 8 is going to be -2 over -2 plus 1 is -1. So -2 over -1 is 2. For this one, we're going to use x equals -1. So we cover up x plus 1. We have -5 plus 8 is 3 over -1 plus 2 is 1. So 3 divided by 1 is +3. So there is our partial fraction decomposition. Now we do the integration. So it's going to end up as 2 natural log of x plus 2 in absolute value plus 3 natural log of x plus 1. And that's going to all be evaluated from 0 to 1. So let's finish this up then. So we're going to end up with 2 times the natural log of 1 plus 2 is going to be 3, plus 3 natural log of 1 plus 1 is going to be 2. I'm not writing in the absolute value because 3 and 2 are already positive. Now I'm going to plug in 0. So we have 2 natural log of 0 plus 2 is 2, plus 3 times natural log of 0 plus 1, which is 1. All right. So what do we got here? We've got 2 natural log of 3, no more natural log of 3s. And we have 3 natural log of 2 minus 2 natural log of 2. So that's going to just be plus natural log of 2. And then we have minus 3 natural log of 1. And my question to you is, what is the natural log of 1? Natural log of 1 is saying e to what power equals 1. And the answer to that question is 0. So this is really just 3 times 0. So that really just goes away. Our final answer is 2 natural log of 3 plus natural log of 2. That was 0. Okay, so that's it. That's how you do partial fractions. Thanks for watching. Make sure you submit the notes and have a great day.